In this tutorial, I will show how to implement a functional language using Scala. The language I will implement is a small subset of Dhall. Dhall is not very well known. It is a purely functional configuration language. This is the official website. It explains how to use Dhall to manage configuration files in JSON and YAML. Programs in Dhall look like this. You can see this is a functional language similar to Haskell. The syntax is very minimal, but it is nevertheless easily readable. Functions are applied to arguments with just a space. There is no parentheses necessary. That is typical for languages like Haskell, OCaml, F#, and some others. So this Dhall program is just one big expression. Let f equals something, let id equal something in something else. So entire programs are always single expressions. All expressions are statically typed. There are very few built-in types. The language is intended for configuration management, so it has no side effects. There is no mutation. All variables are constants. There are no exceptions. There are no side effects. However, the type system is so powerful that one can implement pretty much all the idioms of functional programming. In addition, Dhall implements structurally typed records and union types, and even has some basic support for dependent types for very narrow use cases. The Dhall language does not support arbitrary recursion, so all computations in it are guaranteed to terminate. It also has a module system based on importing files, and one feature that it has is that all expressions are computed to a symbolic normal form. In other words, the evaluation also happens under a lambda. So that is to say, a function body is also simplified if possible. So here's an example how one can implement a Dhall script to create a configuration file which would look like this in JSON or YAML. One would make some definitions and then read, let's say, username and password from environment variables, perform some validations, and then create a configuration structure, which is a record, and then this record would be translated into JSON or YAML. So this is essentially how Dhall is positioned as a configuration language. We will take a very small subset of Dhall, which I call µDhall or µDhall. µDhall has just enough features to run the first example here. You can define functions, you can perform some arithmetic with natural numbers, and you can type check everything, and that's about it. So in order to implement this functionality, we're going to have just 9 different types of expressions. So let me show you an example program that has all these features. So we do have type parameters if we want to. These are variables of type. Other than that, there's not so much you can do. There aren't going to be any records or any union types or any imports. We're just going to implement the pure basics. So there are only 9 types of expressions, a constant number. We're only going to support natural numbers. A constant built-in symbol, such as type or a built-in function, so we will implement a built-in function. Natural subtract, variable symbols. Now, in Dhall and in µDhall, variables may have an index, and index I will explain in detail, but very briefly, it's a De Bruijn index, but it is attached to a specific name. So consider this definition of f. It has a lambda x and then again lambda x. So in most languages, the outer x would no longer be accessible in the body of this function. But in Dhall and in µDhall, we can put an index. So we say x at 1, and that refers to the x which is 1 outside of the innermost x. So in this way we can use variables that have the same name, and this does not create ambiguity as long as we have the indices right. So this is the way that Dhall simplifies the problem of renaming variables, given that in this language we have to perform symbolic evaluation. So we need to be able to substitute things symbolically. And so variable symbols may have an index, but I will talk about this in more detail later. Then we can have an expression that is annotated explicitly with a type. We can have a lambda function. We can have the type of a lambda function, which is written like this. For all a of type t, return type b. We can have a let expression, let x equals a in b. We can have a function application that's written, as I said, just with a space, doesn't need parentheses. And we can have binary operations. We'll implement just two. We'll implement plus and times. So here we start implementing by saying what are going to be the symbolic constants, or the constant symbols. The constant symbols are going to be just these 5. The natural is going to be the name of the type, natural. Natural fold and natural subtract are going to be built-in functions for working with natural numbers. And type and kind are type symbols. So the type system in this language, the µDhall is going to be just that you have say numbers, they have type natural. The type natural itself is a symbol that has type, and that type is called type. The symbol type itself has a type that is called kind. So that's how that is built up. Because everything needs to have a type, and also the type symbols need to have a type. And the only exception is that the symbol kind does not have a type. And so the programmer will not be able to work so much with the symbol kind itself, which in practice is not a big problem. But this is a way that the type system is built up. We're going to support 2 different binary operations, plus and times. So having implemented them, we will learn how to implement any other operations of this kind. Or if we need any more constant symbols, we can also add. But for now, these are going to be what we implement. So here's the main expression type. I'm going to just implement it in a very straightforward way. I'm going to have an algebraic data type for all expressions that just writes down what the expression is. No tricks. So we have natural literals, we have variable with De Bruijn indices, we have a lambda function, we have a function type, we have a let expression, we have an annotation applied, which means it's an application of a function to an argument, and we have built-in constant symbols and binary operations. So the binary operation is parameterized by the operator, and so we have two operators here, and now we see in this way we can more easily add new operators. We wouldn't have to change this type anymore as we add more operators. So to test this, let's just write down some expression, and this expression is 123 plus a. So that's how we will do it. It's quite verbose, of course, but we will deal with that a little later. Now, one interesting thing that we can do with this expression type, and that will be really helpful for later implementation, is to implement a map method. Now, the map method usually requires type parameters. In this implementation, we don't have any type parameters. So why would we need a map method? Well, because we see that this expression type is recursive, and it has recursive parts that have the same type expression. So often we will have functions that transform one expression into another, and this function will be recursive so that we'll transform all the arguments in the same way. So for instance, if you have a function that's applied to an argument, then a transformation will first be applied to the function, and then it will be applied to the argument, and the expression will remain in the same structure. So this is going to be used often. So that's why I want to implement a map function. So what does the map function do? It will map all the nested expressions. So if you have, say, a natural literal or a built-in or a variable, then we don't change anything. Now this comment, this was a different implementation that I don't actually need. This was actually a recursive implementation of map. I would perform this substitution to all levels, but I thought I would need it, but actually I don't, so I have a much easier non-recursive implementation here. So you see, if say we have a lambda, name remains the same, but type and body are transformed through this function f. So there is one layer of transformation that is being applied here. So now the next step is that it's of course very verbose to write expressions in this way. So let's introduce a little language, and the language is based on wait a second. This Jupyter notebook is acting up. So the language means I'm going to write down expressions of the language in a shorter way. So for example, instead of saying variable name 0, I would just say variable dot exclamation mark. And this way I will more quickly create expressions in this language. So for example, here is a test. So I would say just 1 plus 2 times 3. So it would be written like this. So instead of all those case classes, I will just write these operators. Now this is just good for testing, because very soon we will implement parsing and we will not have to write these expressions. But this is useful for tests, and so let me just put it here. Now the next operation we're going to implement is pretty printing. Now pretty printing is not very easy in this language because there are different precedence operations. And let me show you how the pretty printing can be done in the most general way. The idea is that different operations have different precedence with respect to what is outside of them or what is inside of them. So we introduced the concept of inner and outer precedence. For each expression has different levels of precedence when you look outside and when you look inside. So precedence are just integers, and higher values mean that the operations bind weaker. So for example, the operation times will have precedence 10, and the operation plus will have precedence 20. So let's look at first example. Let's say an expression like this, a times b plus c. Now the sub-expression b plus c has precedence 20, and outer precedence means that to the outside, to the outer expression, we expose the precedence number 20. The operation times has precedence 10, and so it means also it gives the precedence 10 to its arguments. And so that means that outside of b plus c, we have precedence 10, and inside precedence 20. And that forces us to put parentheses, because 20 is greater than 10. So we then formulate a general rule. If a sub-expression has an outer precedence that is strictly greater than the inner precedence of that sub-expression in the enclosing expression, that's when we put parentheses. We put the precedence for constants and variable symbols to 0, so then that will never be greater, and so then they will never need any parentheses. So then the task is just to find out what are all these outer and inner precedences for each expression and for each sub-expression, so that the results are what we want. So here are some diagrams to help us to see how that works. So for example, the expression a plus b times c corresponds to the case classes plus of a times bc. Now plus exposes precedence 20 and times precedence 10. So that means that the argument of plus, which is b times c, is a precedence 10 expression, which is inside a constant a context which has precedence 20. So there is no parentheses necessary. But in the other example, where we have star and here we have plus, we just exchange plus and times. Times puts its argument in precedence 10, and plus exposes precedence 20 to the outside, and that is greater. And so it means that the plus must be in parentheses. So here are some more examples to show how this works for different expressions. But for instance, here we have f applied to a value which is g applied to c. In order to put parentheses here, we must expose different precedence levels to the outside and to the inside of application. Otherwise, if they will not be greater, and there won't be any parentheses according to the algorithm. So this sub-expression applied gc exposes outer precedence 5 to the outside, and this expression applied f something puts that something into precedence 4, and so that is 5 is greater than 4, and so then we have parentheses here. And so similarly, you see that these expressions expose inner precedence, so the arrow to the right, I mean by that is the inner precedence, which is that inside a big expression there is a smaller sub-expression, and that smaller sub-expression has the inner precedence 10, but that sub-expression itself exposes certain precedence outside, which is its outer precedence. And then comparing these precedences, we mechanically put parentheses in the right places. So I will not go through each of these examples in detail, but essentially that's the idea. So we need to find for each data constructor what precedences will be the outer, and for each of its arguments the inner precedence. So for instance, it means for the lambda we have two arguments. For each of them we need to specify the inner precedence, and then we have an outer precedence for the entire lambda. So it turns out that for lambdas a big value is good, but for instance, for applied, there must be small values, but they must be not the same. So this is exactly what I was showing you in this example. So having made these precedence levels to our liking, we can implement the precedence algorithm. So the main function here decides whether to put parentheses. So it says I have an expression which is already printed, and so it's a string, it's not an expression type, and I just need to decide whether to put it into parentheses or not. In order to decide that, I need to know the outer precedence and the inner precedence. And so if outer precedence is greater than the inner precedence, then I put parentheses. And then we have the main prettyprint function, which is that we compute or we look up the precedence of the expression, which is just fixed for each data constructor. We need to write down what that is. And then we say, well, if it's a natural, literal, or variable, then we don't need to do anything. But if we have anything like lambda and so on, then we print using the inner and the inner precedence for the two arguments. We print the arguments, and then we need to print the entire result in precedence that is given to us. So that is the way that this works. And now let's test it. So we had these expressions that I defined before, and they must be printed like this. And then you see here a compilation fail, but this is because I have not run the notebook. Let me run it. And it should not fail. Yes. So this is the first session where we found the expression language and implemented the pretty printer.